In this screencast, I'm going to illustrate a Markov process and how you can use transition matrices to find future states as well as to find steady states in a Markov process. So the idea is, suppose we have a car rental company. So we rent cars. And suppose we have two different stores. We've got one in Rexburg, one in Idaho Falls. And we've been keeping track of data for the last few months, and we've noticed that every week when we rent a car in Rexburg, 60% of those cars end up in Rexburg at the end of the week. 40% of them end up at the IF store. In the Idaho Falls store, 80% of the cars that we rent in the Idaho Falls store stay in the Idaho Falls store, and 20% of them end up coming back to Rexburg. So these two stores have some cars, and the cars that we rent end up going to different places. So let's suppose we have 200 cars. And suppose initially, right now, that we've got 100 cars here and 100 cars in Idaho Falls. So we got 100 cars in both places. Question: after a lot of weeks, how many cars are going to be in each spot? So our goal right now is to turn this into a problem involving matrices, and we're going to discover that eigenvectors show up as a solution to the long-term problem of where will all the cars be in the long run. So first, we're going to start with setting up a system of equations. The idea is 60% of the cars that are in Rexburg stay in Rexburg. I'm going to write down Rexburg new. I'll write R new. The cars that are going to be in Rexburg in the next week come from what was originally in Rexburg, and we take 60% of those. And then we also have what was in Idaho Falls, and 20% of those end up coming to Rexburg. Now in the Idaho Falls store, the amount of cars in the next week is, well, 40% of the ones from Rexburg. So the remainder, 40% end up from Rexburg, end up in Idaho Falls. And 80% of what was in Idaho Falls end up in Idaho Falls. I'd like to notice that that sums to 1 and this sums to 1 as well. So here's the idea. We're going to turn this into a matrix. And the matrix equation we have is, we've got a 0.6, a 0.4, a 0.2, and a 0.8. I can think here's Rexburg, here's Idaho Falls. This is the percent to Rexburg, this is the percent to Idaho Falls. And if I just take these coefficients and I multiply by Rexburg and Idaho Falls, I get out the new Rexburg and the new Idaho Falls. You can think of this as our current state. And then 1 week later, this is our next state. So if currently we have 100 cars in both, then we can find what happens in the next week. So if this is current, then the next week is simply matrix multiplication. I take that 0.6, 0.2, 0.4, 0.8, and multiply by our current state, which is 100, 100. And out pops 60 plus 20, or 80, and 40 plus, that is 120. So this is 1 week later. Well, what if I want 2 weeks later? So 2 weeks later, assuming that this percentage remains the same, 2 weeks later what happens is, well, I take the previous week, so I've got this 0.6, 0.4, 0.2, 0.8, and now I just multiply by what our current state is, which is now the 80, 120. And then if I multiply that out, that's 60% of 80, that's 48 plus, and then 20% of that, 24, and then we've got 32 plus 0.8, 96. Let's see if my arithmetic's going well. That's 72 and 128. And so this is 2 weeks later. Well, I could continue doing this, and I can get as many weeks later as I want. You can look at this also as this is actually just take our matrix, times it by the matrix, and then the initial state, I'll write x naught. So this is the same thing as taking the matrix squared and timesing it by where we started. So 3 weeks later is a cubed x naught. N weeks later is a to the n x naught. Notice that I'm using powers of matrices to do that. So the question is, limit as n approaches infinity of an x naught equals what? Is there something, some end state is what will happen to the total number of cars? Will all of them end up in Idaho Falls? Will all of them end up in Rexburg? Where will the cars be? To answer that, what we're going to do is we're going to look at something called the steady state. Really, if I have found the steady state, then if I take the matrix and times it by my steady state, I ought to end up with my steady state. Hold on, wait a minute, I just wrote something down. And there's a 1 right there. This is the same thing as, can I take a matrix times by a vector and get a scalar times a vector? That's eigenvalues. Because the columns of this matrix each sum to the number 1, the number 1 will be an eigenvalue. So our goal, find eigenvectors. Lambda equals 1. I'm not even going to find the eigenvalues. We'll discover in the next unit why 1 has to be an eigenvalue. For this, at this point, we just want to use the fact that it's an eigenvalue to find the eigenvectors. So I'll take the 0.6 minus 1, 0.2, 0.4, 0.8 minus 1, which is negative 0.4, 0.2, 0.4, negative 0.2. It's augment by 0. And now we'll reduce. I think it's probably easiest if I get rid of the decimals. Notice that the bottom row is a multiple of the top. I'll ignore it, and then I'll divide this one by 4, which gives me, I'll divide by negative 4. Positive 1, negative a half, 0, 0, and then 0, 0. So what that tells me is that my eigenvector is 1/2 1. Remember, this just says x minus 1/2 y is 0, and y equals y because y is a free variable. So x is 1/2 y. That's why the 1/2 went there and the 1 went there. So I've got an eigenvector. Well, that eigenvector tells me that the ratio of Rexburg to Idaho Falls is 1/2 to 1. If I double each of these, remember that eigenvectors can be multiplied by any scalar. This is 1 to 2. So for every 1 car in Rexburg, there'll be 2 cars in Idaho Falls. Well, if I sum those, I get 3 and divide by it, 1/3, 2/3. This is now the percent of cars in each spot. 1/3 of the cars are in Rexburg, 1/3 of the cars are in Idaho Falls. Well, if I take 1/3 of the cars and times it by 200, that gives me 66.666 in Rexburg. So 66 or 67 cars in Rexburg, which means the remaining 133.3 are NIF. That completes the screencast.